For decades, the sound barrier was the ultimate frontier. Then came the supersonic era, characterized by sleek jets and roaring engines that could outrun their own thunder. But as of 2026, the world has officially crossed the threshold into a terrifying and unpredictable new regime, the hypersonic arms race. We aren't just talking about fast anymore. Hypersonic weapons move at Mach 5 and beyond, speeds exceeding 3,800 miles per hour. At these velocities, the very physics of flight changes. Air becomes a viscous, searing plasma that can melt traditional airframes. These weapons don't just travel in straight lines. They maneuver unpredictably through the atmosphere, skipping off the edges of space like stones across a pond. They are too fast for traditional radar to track effectively, and far too agile for current missile interceptors to hit with any degree of certainty. But the real shock of 2026 isn't just the sheer velocity, it is the crushing economic reality of this new warfare. The Pentagon was recently sent into a tailspin by the debut of China's YKJ-1000. This hypersonic glide missile reportedly costs a staggering $99,000 per unit. To put that in perspective, that is roughly 1/40th the cost of a single American SM-6 interceptor, the very missile designed to stop it. While American hypersonic programs like the Army's Dark Eagle are multi-million-dollar masterworks of artisanal aerospace engineering, the YKJ-1000 is being colloquially called the cement-coated missile. It achieves its goals by utilizing commercial-grade electronics and foamed concrete for thermal protection. It is a good enough weapon produced at an industrial scale that threatens to overwhelm even the most advanced defenses through sheer volume. The global hypersonic market is currently exploding, projected to grow from $8.7 billion in 2025 to over $23 billion by 2035. To survive this shift, the United States is being forced into a radical pivot. It is moving away from slow, boutique manufacturing and toward a high-tech factory floor, dominated by the magic of 3D printing. The race is no longer just about who is the fastest. It's about who can build the most for the least. The anatomy of a hypersonic scramjet, fire and ice, is how do you keep an engine from melting when it is traveling 7 times the speed of sound? This is the central engineering challenge of the decade. Traditional jet engines, the turbofans you see on commercial airliners, use rotating metal blades to compress air before combustion. But at Mach 5, the air entering the engine is moving so fast that those turbine blades would simply disintegrate under the centrifugal force and heat. Enter the scramjet, supersonic combustion ramjet. A scramjet is an engineering marvel because it has no moving parts. It relies entirely on the vehicle's extreme forward momentum to ram air into the intake. However, lighting a match in a hurricane is a common analogy for scramjet combustion, and it's an understatement. Yet the friction of air at these speeds generates temperatures exceeding 2,000 degrees Celsius, hot enough to turn high-grade steel into a puddle of molten liquid in seconds. The secret to surviving this inferno is a process called regenerative cooling. This is a closed-loop thermal management system that is as elegant as it is complex. Before the liquid fuel, usually a specialized hydrocarbon, is injected into the combustion chamber to be burned, it is pumped through a network of microscopic, hair-thin channels carved directly into the engine walls. In this setup, the cold fuel acts as a heat sink. It absorbs the massive thermal energy from the engine body, protecting the metal from melting. Simultaneously, this process preheats the fuel to near combustion temperatures, making it explode more efficiently once it finally hits the igniter. And it is a delicate balance of fire and ice, where a single blockage in those tiny channels results in the immediate explosive vaporization of the missile. The additive revolution, 3D printing the future. In the past, creating those microscopic cooling channels was an industrial nightmare. Engineers had to mill hundreds of separate metal parts, hand-weld them together, and hope the thousands of joints held under extreme pressure. It was a slow, artisanal process that was prone to leaks and high failure rates. As of 2026, the hypersonic surge is being driven by additive manufacturing, specifically a process known as laser powder bed fusion, PBF. This is not the plastic 3D printing you see in a hobbyist's garage. This is the industrial growing of superweapons. In growing the engine, Instead of starting with a block of metal and cutting parts away, subtractive manufacturing, high-powered lasers melt layers of exotic niobium or nickel-based superalloys. These layers are measured in microns, thinner than a human hair. Complex geometry. 3D printing allows engineers to grow the cooling channels in complex, bionic, or honeycomb shapes. These geometries are mathematically optimized for heat transfer, but are physically impossible to create with traditional drills or lathes. Part consolidation. This is the ultimate bottleneck breaker. A scramjet engine that previously required 300 separate parts and 6 months of specialized labor for assembly can now be printed as one single seamless piece in less than 48 hours. By embracing this commercial shift, companies like Raytheon and the Australian-based Hypersonic are slashing production times by an incredible 80%. This isn't just a cost-saving measure, it is a strategic necessity. The US can no longer afford to build 10 experimental prototypes. It must build the thousands of missiles required to counter the affordable mass of China's YKJ-1000. The $20 billion budget shift. The math of war. The Pentagon has finally recognized the cost asymmetry threat. In the old world of warfare, the US relied on quality over quantity. But the math of 2026 is broken. If an adversary can launch 10 $99,000 missiles for every one $4 million interceptor the US fires, the defender will eventually run out of money and ammunition long before the attacker runs out of missiles. In the 2026 defense budget, nearly $4 billion has been allocated specifically for hypersonic research and manufacturability at scale. The HALO program, the US Navy is fast-tracking the Hypersonic Air-Launched Offensive HALO missile. Unlike previous land-based systems, HALO is designed to be carrier-deployed by 2029, giving the US fleet a standoff capability that keeps carriers safe from enemy shore defenses. The 3D printing mandate. New Pentagon contracts now include a mandatory scale clause. Defense giants are being forced to move their production away from traditional hangars and into mega printer farms. These facilities are designed to churn out scramjet engines with the same consistency and speed that a car factory churns out engine blocks. The logic of the modular factory. It might seem like a stretch to compare a hypersonic scramjet to a commuter car. Still, the industrial philosophy behind the YKJ-1000 and the new US pivot is centered on automotive-scale manufacturing. The YKJ-1000 doesn't win because it is the most sophisticated missile ever built. It wins because it utilizes commercial off-the-shelf COTS parts, standardized industrial sensors, and simplified materials to achieve good enough results at an overwhelming scale. The chassis approach. Just as a car manufacturer uses a single standardized chassis to build thousands of different vehicles, China is using standardized commercial-grade microchips and foamed concrete to ensure it can launch thousands of missiles. They aren't looking for a handcrafted supercar. They are looking for a reliable and mass-produced fleet vehicle. The 90-second workflow. In the hypersonic world, production velocity is the only metric that matters. This mirrors the high-speed optimization of a modern automotive assembly line, where the goal isn't to build one perfect engine by hand, but to ensure that every single unit coming off the line is identical, functional, and ready for immediate deployment. The scale advantage. If you have one exquisite laboratory, you can produce 10 world-class prototypes, but you cannot win a war of attrition. If you have 1,000 automated 3D printing cells, you own the market. The $20 billion hypersonic race is no longer about who has the best scientists. It's about who has the most efficient, scalable factory floor and produce Mach 5 munitions faster than the enemy can build a shield. Speed is the new stealth. The $20 billion hypersonic arms race is fundamentally changing the logic of global deterrence. For the last 30 years, the stealth, the ability to be invisible, was the primary American advantage. But in 2026, speed is the new stealth. If a missile is moving at Mach 8, it doesn't matter if you can see it on radar. You simply don't have enough time to do anything about it. From the cement-coated YKJ-1000 to the 3D printed mega printer farms of the US Air Force, the goal of modern warfare has shifted toward affordable mass. We are witnessing the end of the era of the billion-dollar destroyer and the beginning of the era of the $100,000 missile. As the global hypersonic market climbs toward its $23 billion peak in 2035, the winner of this race won't necessarily be the nation with the most advanced physics labs. It will be the nation that can master the assembly line, harness the power of additive manufacturing, and produce Mach 5 burgers faster than the enemy can build a shield. What do you think? Should the US continue to spend billions trying to build a Golden Dome shield to stop these missiles? Or is the only real defense to build 100,000 hypersonic missiles of our own? Is good enough technology the future of warfare? Or is it a dangerous compromise? Let us know your thoughts in the comments below. And if you want to see the industrial secrets behind the silicon shield or the $120 billion shipbuilding bottleneck, don't forget to hit like and subscribe for our next deep dive into the machines that shape our world.